Well, it seems we have a problem here. As says on your engineering license, Mr. Leonard Euler, that you began practicing in 1723, but then that means you were only 16 at the time. It also says here that at the same in that year you wrote a dissertation and received your Master of Philosophy by comparing the philosophies of Descartes and Newton. I'm not sure I buy that. Please convince me that you're actually this Leonard Euler you claim to be. Of course I can describe Euler buckling to you. My name is Euler. I know this theory and I can tell you the solution. But before we get to the solution, we have to make 5 assumptions. First, we're going to assume that the column is pin to pin. That means that the column is free to rotate at the top, but we're going to keep it from moving in the horizontal direction. Same at the bottom, we're going to have a pin. Assumption number 2, we're going to assume that the column is perfectly straight. Perfectly straight. Next, we'll assume the load is applied perfectly to the centroidal axis. No eccentricity. The point load is concentric with the member. Number 4, we're going to assume that the material remains linearly elastic so that the stress is directly proportional to the strain using Young's modulus. And my 5th assumption is that the buckled shape, the buckled member, will bend about a principal axis. If we use those 5 assumptions, we'll be able to develop the differential equation for buckling of the member. Well, hopefully you managed to get those assumptions written down, but if you didn't, pause the video right here and write them down. We're going to move on to equilibrium. So let's go through the derivation of Euler's column. So we're looking at buckling Euler style. So for equilibrium, I want to imagine the displaced shape of this column. So we know buckling will display something like this. I've sketched it here in green under the applied load P. The beam has properties, modulus of elasticity E and moment of inertia I, as well as the length L. Now I'm going to consider at mid-span. Mid-span here will have some sort of deflection delta, and it doesn't really matter what this delta is, just know that we have some sort of displacement mid-span. What I want to do is I want to come to mid-span here and I want to make a cut and draw a free body diagram. So I know you guys are just missing this from statics days, so I'm going to appease you by making a free body diagram of the cut right here in the middle. Now remember, we talked about this as being a bifurcation of equilibrium. Basically, we could have 2 possible equilibrium states. And so to derive our formula, we're going to need to sketch our deformed shape, our possible deformed shape, and come up with what force is going to cause this deformed shape to happen. Alright, so I look inside my circle, and for my deformed shape I have this column. I've sketched the column in black. I moved my x and y axis over here. I'll put a dashed line in here for the original shape of the column, which was straight, perfectly straight, according to our assumption. And we apply the load P as shown. Now, of course, when we make a cut, we have to have 3 forces, 3 internal forces, right? This is the axial force, the moment, and also shear. Now I've cut the beam at mid-span, so technically in this case the shear will be 0. If we don't cut at mid-span, then our axial force P and our shear would have components, and it just makes the derivation a little bit more messy. So I'm going to cut at mid-span so I can kind of get rid of this shear from our derivation, just to make it a little bit simpler so we can just kind of get the concept down of what's happening here in Euler buckling. I've also sketched my internal forces in the direction that they need to be for equilibrium. Alright, so I'm just going to jump ahead to my equilibrium equations, and I'll look at summing my moments about the cut. If I sum my moments about the cut, I get the moment m applied at the cut minus the load P in orange applied
times some distance, and whatever distance that happens to be. Now, very generally, I can call this distance y. If I look at my xy axis, the distance is going to be the value of y. That pretty much wraps up my moment equation, so I get that m minus py has to equal 0. Now, recall from Euler-Bernoulli beam theory, that also has Euler's name in it, don't forget that, that we said that the moment was equal to negative ei y double prime. And so if I plug this now into the equation, I would get ei y double prime plus py equals 0. So I just multiplied everything by a -1 to get rid of that negative sign. All right, so I'm substituting that value into my summing my moment about the cut. As you can see, this is what's classified as a differential equation because I now have a derivative of y tucked away inside my equation of equilibrium. I can rewrite this by dividing by ei, so I get y double prime plus p over ei times y equals 0. And that then leads me to the following condition. I can look at y double prime. I'm going to write this as y double prime plus lambda squared y equals 0, where I let lambda equal the square root of p over ei. Now you might think it's crazy that I'm doing this, but I have a method to my madness. If you're good at differential equations, like I know you are, y double prime plus lambda squared y equals 0 is a differential equation maybe that you recognize. If you don't, you could go through and you could solve for the homogeneous and the particular solution and go through. But I'm just going to jump ahead here and let's look at the general solution for this equation. So our general solution says that y of x equals a sine lambda x plus b cosine lambda x plus cx plus d. Again, where lambda equals square root of p over ei. To help us solve for a, b, c, and d, where these are just random coefficients, we're going to need some of the derivatives. So go ahead and you can look those derivatives over. Don't forget, as you're coming up with these derivatives, to do the chain rule. So that's how we get that lambda out in front. We get the a lambda cosine lambda x. And each time you take a derivative, you get an extra lambda multiplied times the coefficient out in front. Now we have to define some boundary conditions for the problem, and so we're going to need to refer back to our Euler column picture above. So we can take a look at this picture, and we want to come up with some of the boundary conditions. Now these boundary conditions are going to be very similar to how we looked at beam deflection boundary conditions a couple lessons ago. All right, transitioning back to our boundary conditions on page 21-3. We see that we can say, well, we know the deflection at the top has to be 0, so that translates to y of 0 equals 0, because the movement in the y direction for the deflected beam is 0 at the top. Likewise, we know that at a pin, like we did for beam bending, we said that the moment has to equal 0. So strictly speaking, ei y double prime of 0 has to equal 0. And this implies that the moment at the top has to equal 0. What other boundary conditions do we have? Well, I would tell you, let's look at the bottom, at the pin at the bottom, right? We know the deflection at the bottom is 0, and we also know that the moment at the bottom is 0. And so we can go ahead and write the boundary conditions y of L equals 0 and ei y double prime of L equals 0. And we'll go ahead and write what those mean. All right, so this is how we come up with our boundary conditions. Any kind of version of using deflection, we'll have to use slope eventually, and maybe moment or shear we can use to come up with the boundary conditions. Once we have the boundary conditions, we can go ahead and use the general form of the solution to the differential equation to solve for the variables a, b, c, and d. Remember, a, b, c, and d are constants. So I'll start with condition number 1, y of 0 equals 0. So that means a sine of lambda times 0, which is a sine of 0, plus b cosine 0, plus c times 0, plus d has to equal 0. All right, so sine of 0 is 0, and c times 0 gives us 0. So this now gives us b plus d has to equal 0. I don't know what b and d are yet, but I know that together b plus d has to equal 0. I can move on to boundary condition 2, so ei y double prime of 0 has to equal 0. So that means negative a lambda squared sine of 0 minus b lambda squared times cosine of 0 has to equal 0. Strictly speaking, I should include my EI, but since EIY double prime of 0 equals 0, then I can divide by EI, and that basically says now that the equation here has to equal 0. So I can divide the EI. 0 divided by EI is going to be 0. Simplifying this, I know sine of 0 equals 0, cosine 0 equals 1. So this now gives me that b has to equal 0. If b is 0, and then I substitute this back into my result from the first equation, then that means that d also has to equal 0. So now I've solved for two of my constants, b and d, both of which have to be equal to 0 in this particular case. Let's look at boundary condition number 3. Y of L has to equal 0. So y of L equals a sine lambda L, now b is 0 already, plus c times L plus d, but d is 0 as well. So this gives me the following equation. So I can solve for my constant c in terms of a as a negative a sine lambda L divided by L. And I'll just save this result for the next part of my derivation. In boundary condition number 4, we said that the moment at the bottom has to equal 0, or ei y double prime of L equals 0. So ei y double prime equals negative a lambda squared sine lambda L all times the quantity of ei, and that has to equal 0. Well, that's interesting. How can that equal 0? Well, there's a few different possibilities, so I'm going to look at them all. First, let's look at EI. What if EI equals 0? If EI equals 0, we call this a trivial solution, because that means that the modulus would basically be 0, or the moment of inertia would have to equal 0. So that implies the beam has no stiffness. So if the beam has no stiffness, what business do we have using it in any sort of engineering application? So the beam has to have a stiffness if we're going to use it to build something in engineering. So E and I have to have a value. Next, what if A equals 0? So what if our constant A equals 0? Well, if A equals 0, we see in the above equation, then C, the constant C, would have to equal 0. So then that means A, B, C, and D are all equal to 0. And that doesn't really give us a good solution to our differential equation. If all our constants are 0, then obviously 0 equals 0. Let's consider lambda squared equal to 0. So we know that lambda squared is p over ei. So if this is 0, that means that the load P is 0. Well, if the load P is 0, then of course we're not going to have any buckling because there's no load on the column. Or this could also imply that EI was equal to infinity. But if we have an infinitely stiff beam, then it's not going to buckle. If E and I are basically infinity, we're not going to have a buckling problem here. So that leaves us one final interesting solution when sine lambda L equals 0. So when does this occur? This occurs whenever lambda L equals 0, or it could equal pi, 2 pi, 3 pi, 4 pi, or all the way up to n pi. Well, the first answer, lambda L equals 0, that's trivial. Again, that implies P is 0 or EI is infinity, or that the length is 0. So I want to look at the next one, when lambda L equals pi. That gives us an interesting result, because sine lambda L can equal 0 when lambda L equals pi. And that's going to happen at a very unique value for the load P. And so that's going to give us what we call our critical buckling load. So we'll set lambda L equal to that first mode of failure pi. So lambda is square root of P over EI times L equals pi. So I can rewrite this by taking L to the other side and squaring it as P over EI equals pi squared over L squared. And rewriting it for P, I get that P equals pi squared EI over L squared. So this is what we call the Euler buckling load, or our P critical, the force at which we expect buckling, according to Euler, is, for this particular column, pi squared EI over L squared. So when the critical load is equal to pi squared EI over L squared, our column can either remain straight or it can be deflected into that buckled shape that we sketched on the previous page. Let's take this one step further to look at the buckled shape. We know that y of L is somehow related to the sine function, so we're going to get sine curves for our buckled shape. So let's see how we can look at the different modes of failure when n equals 1, pi or 2 pi or 3 pi, to see how we can draw the deflected shapes.
Let me further explain the sine curves to you. When we have n equals 1, then we get one buckled shape, one sine curve for our member. However, if we look at higher modes of buckling, we get more than one sine curve. So we get the buckled shape is going to look something like this. Now, why is this important? Well, by looking at higher modes of failure, we know that we can find the ideal spots for our braces. So at the second mode of failure, we see that the sine curve is over half the length, so I should apply a brace here. So if I look at the third mode, then I would have multiple braces, and then my column would buckle in 3 curves, but I only have 2 hands, and my hat's falling off. So that's all I have for you now.
As we saw in that demonstration, we saw that when we added braces in the middle, we were able to buckle at higher modes. So oftentimes we like to include braces at different points along the cross-section to increase the buckling capacity of our columns. We can find the ideal spot for these braces by looking at the higher order modes of failure. Obviously, when n equals 1, that is going to give us our first mode of failure. But if we look at n equals 2 or n equals 3, these are then the optimum spots to place our braces so that we can get more sine curves or a higher order buckled shape. Finally, I just want to look at the equation pi squared EI over L squared. I want to make some comments and observations. So the first one is I want to talk about strong axis versus weak axis buckling. So for an I-shaped member, a strong axis buckling is not going to control for a given length. So we see that P critical increases as our moment of inertia increases. So these are directly related to one another. Because most cases, strong axis buckling has a much larger moment of inertia I than weak axis, then when we have a prescribed length, so when the strong axis and weak axis buckling length are the same, then weak axis buckling will control. In addition, when we look at this formula, we see that as the length increases, P critical goes down. So P critical goes down as the length increases. So the longer a member is, the more susceptible it is to buckling. So that means the length, or what we'll call the effective length, is an important contribution. It kind of plays a big role in determining what the critical buckling strength is for a column. Finally, I want to note that P critical is not related to the strength of the material. It is independent of Fy, or our yield strength, or our ultimate strength. It's independent of all of these. P critical relies upon E and I and the length. And so we see that it's mainly a geometric effect. Of course, E, the modulus of elasticity, is tucked away in there. But we see that it's independent of Fy, which is kind of unique. Alright, so that brings us to our general procedure. So you can look over the general procedure to solve this problem. And I'll catch you in the next video when we hopefully look at an example. And hopefully this will prove to our cop that we actually know how to solve these buckling problems.